Okay, example 4. Limit as x approaches infinity of the square root of x squared plus 1 minus x. Square root of x squared minus plus 1. If x gets substituted in here, I'm going to get, if I just put infinity in for x. Infinity squared plus 1 is infinity squared plus 1. Square root of that's about infinity, right? We're subtracting from that infinity, so we get infinity minus infinity, which equals 0, right? That seems like a reasonable answer. Infinity equals 0. Okay. Unfortunately, infinity minus infinity does not necessarily equal 0. It could. Might equal 2/3, might equal 77, could equal negative 513 pi over 2. I don't want to see that problem, but it could. It could equal negative 513 pi over 2. The point is, infinity minus infinity is indeterminate. You don't know what it equals. There's no way to determine it. The other problems were infinity over infinity, still can't determine it. So that's the problem each time. How do we fix it? This specific situation, once we've established this, the way we fix it is we multiply by, I'm going to make it a fraction. I want rational structures when I'm dealing with infinity. Rational meaning fractions. Why? Because fractions are easy. That was easy, right? Example 1, fraction, easy. Radical with fraction, still easy. Radical with fraction approaching negative infinity, still easy, right? Rational functions are easy when we're dealing with infinities. So put it over 1 and then multiply top and bottom by something. Now we could just multiply top and bottom by 6, that'd be something. But we want to be more productive in what we multiply by. So when you deal with a radical structure and you want to create some rational thing out of this, the best thing to multiply by is the conjugate. Again, using good algebra, multiplying the top of the fraction by something, got to multiply by the bottom by the same thing. Can't break rules of algebra because we're in calculus. You still have to follow all the rules. What I'm doing is I'm irrationalizing the denominator. I'm going backwards from back in Algebra 1 and Algebra 2. We rationalize the denominator. So I told you all about this queasy feeling you get in your stomach when you do these rational functions and you get square roots at the bottom. You don't like that look, right? You probably develop that queasy feeling now. You see that, I don't like that. We're going backwards from our beliefs here, but that's what you want to do in this specific case. If you get infinity minus infinity, this is how you handle it. Multiply by the conjugate. And that's going to give me limit as x approaches infinity. Alright, so if I multiply the top out, if I multiply a difference and the sum of the same two things, it's just a FL of FOIL, right? The outside and inside products cancel. Positive x squared of x squared plus 1, negative x squared of x squared plus 1 cancel, makes 0, right? Square root of x squared plus 1 times square root of x squared plus 1 makes x squared plus 1. Negative x times positive x makes minus x squared. All that's over the square root of x squared plus 1 plus x. Okay, and this one just happens to do some nice stuff for us. X squared cancels x squared. And we're left with 1 over the square root of x squared plus 1 plus x as x is approaching infinity. Right? What's the highest power of x? X. X to the first, right? That's x to the first, x to the 0, x to the first, and x to the 0, right? So I'm going to multiply top and bottom by 1 over x. On the bottom, I'm going to multiply by either the square root of 1 over x squared or 1 over x, depending on what the structure is. This is a radical, so I multiply by this one. That's not, so I multiply by that one. You just know that if it's a radical, you got to multiply by this structure, not a radical, that structure, and we got both those types of things on the bottom. That's a comma. I don't know if that's good math as far as writing that down, but let's make a semicolon, makes it look more official. But again, we're multiplying by 1 over x, which is both of these, but we have two different structures on the bottom for terms, so we want to have both structures to be able to multiply by. X is approaching a positive infinity, so all that thought about sign is irrelevant. We don't care because that's positive, everything's good. So we just go ahead and do this. We're going to get limit as x approaches infinity of 1 over x on top over the square root of x squared times 1 over x squared is 1, 1 times 1 over x squared is 1 over x squared, and 1 over x times x makes 1. Again, be careful that this is a radical, so it's being multiplied by the radical part. This is not a radical, it's being multiplied by the not a radical part. So again, that's all I'm trying to show you there. The end result of all this stuff is now as x approaches infinity, 1 over infinity on top makes 0. 1 plus 1 over infinity is going to be 1 plus 0 plus 1. So we get 0 over 2, which equals 0. So in this case, infinity minus infinity happened to equal 0. Right? Suppose there was like x squared plus 2x plus 1, x squared plus 2x plus 1. Well, now all of a sudden this is x squared plus 2x plus 1, right? 2x plus 1 would have made 2 plus 1 over x, and all of a sudden it's 2 over 2, which equals 1. So it doesn't have to equal 0. It'll still be infinity minus infinity. So keep that in mind, that just because you see infinity minus infinity doesn't guarantee it's 0. Sometimes it is. Sometimes it's something else. So keep that in mind. Work through the process correctly. The problem types you'll see tonight are either going to be basic rational functions, radicals approaching positive or negative infinity, and then you might get a infinity minus infinity structure. That's how you handle it. Again, make an irrational denominator to create a rational function, and then you can go ahead and go from there. Do it the fraction way.